right, let's get started. Welcome to the second quantum computing session and the last session of POPL. I'm very happy to introduce our first speaker, Abtin Molavi, who is going to be telling us about generating compilers for qubit mapping and routing.
Okay. Yay, last session. So this work is all about trying to automate the process of developing compilers for new quantum platforms. So the first thing I need to convince you of is that the landscape of target quantum hardware is incredibly diverse and fast evolving. And since we're at POPL, I decided to do that with a constructive proof. So this is Chamberlain Hall at the University of Wisconsin-Madison, which is my home institution. And this is where our physics department is housed. This photo is from 1908, which is a little different from now in that there are 3 quantum computers inside of this building right now. The Ericsson lab is developing qubits based on silicon dots that are called spin qubits. The Safman lab is building neutral atom qubits. And the McDermott lab is building superconducting qubits. So within this single building, there are 3 completely different technologies that are being used as the basis for quantum computers today. That concludes the proof. Okay, so where do compilers fit into this picture? Well, in order to get from an abstract circuit description of the computation that we'd like to perform to the native instructions that are actually executed on this device, we need some sort of compilation step between these 2 things. And today, people have really identified compilers as one of the keys towards quantum advantage, which is this idea of using quantum computers for something that we can't use classical computers to do. And the reason we need to study compilers is that they allow us to maximize limited quantum compute resources. So for the time being, we expect that quantum computers are going to be relatively small scale, and we need to do as much as possible as we can to maximize what we have. And furthermore, and having a good compiler allows us to estimate what resources we will need in the future in order to execute larger scale applications and allow us to evaluate proposed large scale architectural designs by targeting them and estimating the resources that they require. Okay, so back to the diversity of quantum platforms. For each of these, we need to develop a new compiler, which results in a zoo of different compilers. So for example, if we have these superconducting qubits that we'd like to target, some quantum circuit we'd like to execute, then we need a superconducting compiler in order to produce a scheduling of the instructions that can actually be executed on this device. So there are several papers that have been written about this problem. And analogously, if we have a neutral atom computer that we'd like to target, we need to develop a neutral atom compiler for it. And there have been papers written on this topic. And then there's another axis along which we design quantum architectures, which is the type of error-correcting code that we want to use. So in order to execute large-scale applications, we're going to need some sort of quantum error correction. And each code also comes with a set of constraints on compilation. So there have been papers that target a particular error-correcting code. So overall, there are many more papers, and there's just a mess of all of these different papers that have been written about compiling for some particular hardware platform. And the goal of our approach is to avoid the redundant work involved in this process of developing a new compiler for every new platform that comes out. And so this is kind of an overview of the system. You write some problem specification, which is a description of a particular platform that you'd like to target in our Amara language. And then our compiler generation process, which is powered by a parametric solver, produces a compiler for that particular platform. And so later you can use that compiler for any particular device or circuit that you'd like to target. And the other part of this paper title, beyond generating compilers, is this idea of qubit mapping and routing. So specifically, we're targeting a compiler pass that's called qubit mapping and routing. And the problem here is that when we write a quantum computation, we typically assume that we can execute any fixed arity operation on any particular subset of our qubits. So that is that a gate can be applied to any set of qubits, and as long as gates are operating on disjoint qubits, then we can execute them in parallel. But it turns out that the reality of quantum hardware is a little bit more complicated than this. So one example is these superconducting qubits that I've mentioned before. So these qubits are fixed in place, and they have coupling with a constant number of neighbors that are local to them. And so if I want to perform a longer range gate, I need to insert swap operations that move my data around on the device. And then each 2-qubit gate has to be executed along one of the edges that appear in this graph that represents the connectivity of the architecture. So once we are implementing an error-correcting code, now we are using several physical qubits in order to encode one logical qubit. So now each of our logical qubits of our circuit is represented by like a 2D patch that consists of many physical qubits. And here, in order to execute gates, we are able to do them in a long-range fashion by constructing a path between the 2 qubits that the gate acts on. But the constraint is that simultaneous paths cannot cross. So I have this logically parallel gate between 2 different qubits, and right now it's blocked because the ancilla space in the middle is being used for a different gate, so it cannot execute in the same time step. It needs to wait for the next time step, and then it can be executed. As another example, we'll turn to these neutral atom qubits. So neutral atom qubits don't have this constraint that they're fixed in space. Over the course of your computation, you can move your qubits around. So I can do something like this. There are certain rules about rigid movements that I can do in space. And then once qubits are within a certain range, they can interact with each other. So the details of these different platforms vary, but you can see how if we zoom out like this, we really get 3 different variants of the same problem. And this problem turns out to be an NP-hard combinatorial problem in all of these cases, and it typically is, which is that I have a circuit and a device, and I'm looking for a scheduling of the circuit which has minimal routing overhead. So you can think about that as trying to maximize the parallelism of our execution and minimize the number of inserted operations and overhead for moving data around. So our idea is to unify these things. And the contributions of our paper are first a generalized abstract problem that captures these 3 examples and many more examples of qubit mapping and routing problems that allows us to separate which of these are kind of fundamental to the process of executing something on a quantum computer and which of them are specific to a particular platform. We also design a language for defining new qubit mapping and routing problems, which allows us to quickly iterate and generate new compilers, which are powered by our parametric solver. So the exciting thing about these generated compilers is that they can match, or in some cases even outperform, the state-of-the-art handcrafted compilers. And we've already seen a use case for them at Google, which used it to generate a compiler for their surface code-based error-corrected quantum devices. Okay. So I'm going to begin by talking about QPU state machines, which are this abstraction that we use to view all of these different qubit mapping and routing problems as different instances of the same abstract problem. So the key idea here is that we define a state machine of feasible device configurations for each problem. And each state in this machine roughly corresponds to a time step in the execution of a circuit. So what that means is that it carries 2 different pieces of data. One of them is the qubit map, which tells us where the qubits that appear in our circuit are physically located in the device. And then the other is a set of routed gates, which are gates that we are able to execute in parallel and that we are executing in parallel in this time step. So we've seen already an example of one QPU state machine. I've gotten rid of some of the vertices that weren't relevant here. And we saw a transition between 2 states. So we had an initial state where we weren't executing any gates. Then we applied a swap operation in order to transition to a different state, which contained the execution of 2 parallel gates. And that transition was enabled by a swap, which means that we have to pay some cost in order to implement it. But there are many other choices that we could have made by either choosing not to modify our qubit map at all, or we could have chosen a different swap. So there's many options for the transitions that you can take. And further, there are many choices of initial map that we could have started from for mapping our circuit qubits onto our device. So once we have the concept of a QPU state machine, we can define this abstract problem of qubit mapping and routing. So the inputs to the problem are a QPU state machine along with some circuit that we'd like to execute. And what we're looking for is a schedule for executing that circuit. So that we think of as a trace of this QPU state machine that executes a circuit. And we're trying to minimize the cost of execution, so that's the optimization objective. So here I have a snippet of a circuit that we've seen before and a trace that executes it. The total cost of this trace is 1, and we get that by summing the costs of each of the transitions. One of them was this identity transition that didn't modify the qubit map, so we didn't have to pay any cost for it, while the other was a swap, so we did pay a cost for it, leading to a total cost of 1. And you can see that each of these gates, these 2 qubit gates in the circuit, are executed along an edge in the graph. So that's the abstraction for abstract qubit mapping and routing. And now I'm going to move on to our language that we designed for specifying new problems. So this language is designed based on a couple of principles that are sort of chosen to be fine-tuned to this domain. So one of them is that we have graphs as a core primitive in the language. So what we noticed is that a lot of these qubit mapping and routing problems model the QPU with some sort of graph. You might have seen that in the pictures that I showed. So this language has sort of, it has first-class concepts for things like edges and paths and Steiner tree construction, and that makes the language unique. Another thing that is kind of a subtle point is that this language is designed ultimately for generating solutions. So the way that we specify constraints is operational. It sort of provides instructions to a future compiler for how they are able to implement a gate, as opposed to declarative constraints that say what are the rules about when gates can be executed. And so we'll see an example of how this allows us to solve things later. And then finally, we want the language to be both easy to use, but not sort of theoretically complex. So it has a pretty minimal syntax, and it's based on like a bare bones functional expression language. So let's look at an example of a program that's written in the Amara language. So we have this block called the route info block. This is the program for the superconducting qubits example, by the way. And the route info block is what defines the constraints for executing certain gates. So this particular route info block defines a constraint for executing the CX or C0 gate. And another way to think about this, to relate it to the QPU state machine, is that it's saying which of the states are valid. And what this block is saying is that each C0 gate must be executed along an edge that appears in the input graph arch. So this is like an implicit argument to the program that is the input graph representing the device. And then we have a second block, this transition info block, which is just telling us what are the available transitions between states and how much do they cost. This particular transition info block is saying that we can update the qubit map between states by inserting a swap gate. And the change in the qubit map corresponds to what that swap implements. So this is an interesting language, and I think it has an interesting semantics. So let's discuss that a little bit now. So a program and a graph together define a QPU state machine. So we saw an example with a grid graph and the program for superconducting qubits. And then when we have a circuit that we'd like to execute, we get a set of solutions for that circuit, which is a set of schedules where every gate in the circuit is scheduled and the dependencies are respected. So together, these three components define a set of solutions. So the way that we formally define the semantics of an Amaro program is as a function from graphs and circuits to sets of solutions, or alternatively as a relation between a graph, a circuit, and a solution that says that this output is valid for the two inputs. So now I'm going to move on to talking about the way that our solver works. And the solver is based on a simple greedy recipe that's at the core of a lot of the handcrafted compilers for individual problems as well. We begin by choosing some initial map for the qubits in our circuit, and then we execute a maximal set of parallel gates. So this means that we try to execute as many gates as we can, and we just greedily add gates to the set of gates that we're executing. Once we've constructed a set that is maximal, we can't add any more gates to it, then we apply one of the transitions that is available to us to get a new qubit map, and then we repeat this process until all of the gates have been scheduled. But the interesting thing about this algorithm, as I've specified it so far, is that there are a lot of these indefinite articles. There's points where we have choices to make. And so the interesting part of this algorithm is deciding which of these choices to make. And our design at a high level is based on searching over the space of possibilities. So what you might see in a typical compiler that's handcrafted for a particular mapping and routing problem is to construct some good choice at each of these branch points using some clever heuristic that's based on intuition about the problem. And instead, we take the strategy of just trying a lot of different choices and taking the best solution that we find. And we implement this discrete search over the space of solutions with simulated annealing. And the nice thing about simulated annealing that makes it well suited to this particular use case is that it's generic. We can use it for all of our different mapping and routing problems. And it allows us a sort of continuous trade-off between the runtime of our compiler and the quality of the solution that we get in the end. And at this point, I want to talk a little bit about what we gain from thinking about mapping and routing problems as programs. And the key takeaway here is that with a program representation of a problem, we can apply program analysis techniques. And that allows us to sort of better understand the space of qubit mapping and routing problems, as well as apply optimizations to the solver that specialize to particular use cases. So an example of this is a property that we define called non-interference. And non-interference is intuitively, a problem has non-interference if the question of whether or not you can implement a gate can be answered locally. So for this example, without error correction, we just needed to check whether there exists an edge between the two qubits, and it doesn't matter what other gates I'm executing at the same time. On the other hand, in this path drawing problem, we saw that one gate can block the execution of another, so the question is not local. This problem does not have non-interference. And by analyzing the program defining these two problems, we can determine whether or not they have this non-interference property. So next I'm going to talk about some of our empirical results. So in order to determine how good our generated compilers actually are, we evaluated on a large range of device models. So we had 7 in total. Some of them are these near-term problems where we don't have an error correction protocol in place. And other ones are fault-tolerant quantum computing problems where we have a large-scale system that's implementing some error correcting code. And we had a benchmark suite of 243 circuits, a pretty wide range of micro benchmarks that are implementing some bits of arithmetic, as well as these famous quantum algorithms like Grover's algorithm and Shor's algorithm. And so for each of these 7 case studies, we generated a compiler with our framework and compared it to some state-of-the-art baseline. And all of the tools were given an hour timeout and some fixed compute resources, and then we report the best solution they find because our simulated annealing search is continually finding solutions. So one example result is this superconducting qubits case I've been talking about. And we compared here to IBM Qiskit, which is this carefully optimized IBM open source compiler framework that has been in development for many years. And what we find in this case is that we are almost as good at minimizing the swap count. So in about half of the benchmarks, we are able to find a solution that's at least as good as Qiskit. But when we look at the estimated success probability, which assigns a probability of failure to each operation, we see that we are strictly better at maximizing this quantity for about half of the benchmarks. So in terms of swap count, it's like we can match in half of cases, but in terms of estimated success probability, we can beat Qiskit in half of cases. So then if we look at an example where here's the distribution of the circuits. Each of these points is a circuit, and points above the line are ones where the Qiskit solution is better, and points below the line are ones where our Amaro solution is better. So now if we move on to an example of a newer proposed architecture that hasn't actually been implemented yet, we can see slightly different results. So here we're comparing against a sort of naive compiler that was proposed in order to evaluate this new architecture for combining neutral atoms 3D space properties with the surface code quantum error correcting code. And so what we find is that our compiler is able to generate better solution in 93% of cases. And so this goes back to one of the motivating reasons I gave for compiler research is that we're using compilers in order to evaluate proposed architectures, and by developing better compilers in this way, we can more quickly get more precise answers about what the right way to move forward in terms of quantum architecture design is. So I'll close with some ideas for future work. So the solver backend I've described is just one possibility for how we might solve these problems once we've defined them using our language. And we're interested in ways of improving our solver using parallelism or reinforcement learning as just two examples. And we're always looking for new problems that we can encode in our framework. I gave the example of the Google compiler at the beginning of the talk. And there's another example with neutral atom qubits where we use long-range gates to implement a different error correction code as opposed to using the movement operations I described. And as part of this process, we're also looking to improve the support for variable gate durations. So what that means is that our current time step implementation sort of implicitly assumes that each gate takes the same amount of time, but we would like to be able to relax that assumption. So I will conclude there. Thank you very much. There are a lot more details in the paper.
Thank you so much. Can I have some questions?
So what is did you try to find out what was the exact complexity class? It's NP hard, but is it possibly, because most scheduling and graph routing problems are actually sit in a higher complexity class?
Yeah, so for individual problems, they have been proven to be NP hard. Our framework is so general that it allows you to you could get an arbitrary complexity by encoding any computation you want in this constraint about when gates can be realized. So it's a difficult question to answer precisely. Like you could say it's undecidable, but that's not very realistic for the types of constraints that would actually come up in targeting a device.
And the second part of the question is the scheduling algorithms from the algorithm side, they work very differently than what you have. If you look at the approximation algorithms for job scheduling and so on. So what is the intuition there? Why are those algorithms very different than what you kind of described? And could you take motivation from that?
Yeah, that's a good question. I'm not super familiar with the approximation algorithms that you're referring to. I think it's always good to look at different places for inspiration. One place where we did find some was in VLSI routing, for example. But I would say one thing that makes this case somewhat different from at least the job scheduling problems I saw in my undergrad was that there are kind of the dependency structure between different things that you need to schedule can be complicated. So,
Let's have one more question over here, and maybe the next speaker can set up.
Thanks for the talk. Do you have anything to say about what benchmarks performed you were able to compile better than Qiskit versus those that Qiskit was better?
So your question was like what kind of circuits we were able to do better? Yeah, we tried looking into sort of the subcategories of circuits we have to see if there were any easy insights there. And I don't have anything clear at this stage, but I can tell you about how that informed our design process. So Ising model circuits are ones that we were doing very poorly on as compared to Qiskit, and we were able to do better by adding an optimization to the way the simulated annealing search is seeded. So the details of that are in the paper, but that was an iterative process of comparing to what's in Qt doing, what we're doing well on and improving based on that.
All right, let's thank Abtin again.